All right, so this video is going to focus on how we determine the concentration of a solution and also how we can prepare them from more concentrated solutions, also known as stock solutions, as well as from solids or salts. So we typically represent molarity with a capital M. This is the most common way that we see concentration expressed. And when it is expressed in this form, it is representing the moles of your solute that have been dissolved in the liters of your overall solution. So when we absolutely know the concentration of a solution, it is known as a standard, and we can use those standard solutions to make dilutions. Adding water to a stock solution, one that's more concentrated, one that we absolutely know its concentration of, and we can determine with knowing the volume of the diluted solution we want to prepare, how much of that stock solution we need to use. So this is using it from a salt. I do it slightly differently because I am not a fan of trying to dissolve a salt in a volumetric flask with such a narrow neck. I usually add it to a beaker and then some water in there and get it good and dissolved, and then transfer it over into my volumetric flask. I rinse out the beaker with a little bit of water just to make sure I've got all the salt transferred. And as you can see, you keep adding water until you bring it up to its calibration mark. And the color of the original solute becomes less intense as it is diluted with the water. If I am making one from a solution, I'm going to determine how much of that concentrated solution I actually need. I'm going to use a pipette to withdraw that amount of that amount of stock solution that I want to transfer and make my diluted solution with. I'll add that to my volumetric flask and then bring it up with water until it reaches the calibration mark. The one exception would be with an acid. You always want to add water to acid, not the reverse. So in that case, I typically would add approximately half the volume of water that's going to be needed to prepare that solution in advance. And then I would add the concentrated acid to that water. At that point, the thermodynamics, if you continue to add water to that acidic solution, aren't going to be nearly as intense. It's not going to be nearly as exothermic, so there shouldn't be the issues you would encounter if you just add all of the water to your acid. So we're going to do some calculations where we determine the concentration of various solutions. We have 4 grams of ammonium chloride. It was dissolved in enough water to prepare 500 mils of solution. We want to know what the concentration is of NH4Cl, and then what are the concentration of its respective ions. You can do these 2 parts separate, or you can do them together. But since concentration is typically expressed in molarity, we need to get moles of our solute and liters of our solution. We have grams of solute and we have milliliters of solution. So we're going to have to do a couple of conversions. And this is going to help you with the last question. If you look at ammonium chloride, you see when it dissociates, it produces 1 ammonium ion and 1 chlorine ion. So everything's in a 1-to-1 ratio. So there's our molarity equation, and we have a quantity in grams that we want to convert to moles, and we have a quantity in milliliters we want to convert to liters. So we can go ahead and substitute those into our molarity expression, or you can find the moles first and find the liters first and then set them into your equation. Doesn't really matter. But if you want to go ahead and do it all at once, you're going to convert your grams to moles by finding the molar mass of ammonium chloride, which is 53.50. So that's going to take care of your grams. And then we want to get our milliliters converted to liters. There's 1,000 milliliters in 1 liter. So the milliliters cancel out, the grams cancel out, and I multiply and divide. I had 3 sig figs in my initial mass, and I had 5 sig figs. I don't know why I have an extra 0 there, sorry. I had 4 sig figs in my initial volume, and I had 4 sig figs in my molar mass. So I want 3 sig figs in my final answer. So me adding that extra 0 to milliliters didn't change anything, 0.150. And because that is the concentration of NH4Cl, and we see that there is one NH4 plus ion and one Cl minus ion produced for every one ammonium chloride, the concentrations of the respective ions would also be 1 to 1. Now, let's say that there had been two chloride ions made through this dissociation process, then you would have doubled the concentration of chlorine. It would have gone from 0.15 to 0.300. Here we have 1 gram of K3PO4. We're dissolving it in 250 mils of solution. We want to know the concentration of K3PO4. And this time I do think you're going to see a difference in your ions. You have 3 potassium ions being produced from 1 potassium phosphate molecule, as well as 1 phosphate ion. So this is going to be set up similar to what I did with the last one. Again, you can do the two pieces separate and then substitute them into your molarity equation. But I'm going to take the grams of potassium phosphate, divide it by my volume, 250 milliliters, convert the grams to moles using the molar mass for K3PO4, and 1,000 milliliters per liter to convert my milliliters to liters. The grams cancel out, the milliliters cancel out. 3 sig figs in my original mass. I should have 4 sig figs in my volume because I don't know why I had the extra 0 again. And I have 5 sig figs in my molar mass. So regardless, the smallest number of sig figs is with my original mass, 0.3 sig figs. So I want to round my molarity to 0.0188. Phosphates concentration will be the same as K3PO4s. They're in a 1-to-1 ratio. But potassiums will be 3 times that amount because there are 3 K pluses generated. So its concentration will be 0.0564. So these last two examples are going to show you how you can do calculations to prepare a diluted solution from a stock solution and a diluted solution from its salt. So we're wanting to take 1 liter of 0.5 molar H2SO4, that's the one we're wanting to prepare. We want to prepare it from concentrated 18 molar sulfuric acid. That is the most concentrated you can find sulfuric acid. So we know what solution we want to prepare, but we don't know how much of this 18 molar solution we're going to need. But because it's a solution, we can measure its amount out in volume as opposed to mass. So we're going to use that dilution equation, M1V1 equals M2V2. If you think about it, when you prepare a mixture of Kool-Aid or Gatorade from a solid, you don't change the amount of solid you've added. The only thing you change is the amount of water. And so if we have the moles, because that's something that we tend to look at in chemistry as opposed to grams in common, then we should have, whether we have a diluted solution or a concentrated solution, the same number of moles that were present originally in our stock solution should also be present in our diluted solution. And that's why we go ahead and multiply molarity times volume, because that will give us our moles. We know the diluted solution's volume, and we know the diluted solution's molarity, 1 liter and 0.5 molar. And we know the stock solution's concentration, 18 molar. So if we use those pieces of information, we should be able to determine how much of that stock solution we're going to need to measure out to prepare the 0.5 molar solution that we want 1 liter of. So these volumes do not have to be in liters. They could be in milliliters. They just have to be consistent. Same thing with your molarities, but you're only going to find that as molarity, so that won't be an issue. So when we solve for V1, which is our X, we see that the molarities cancel out and that we have 2 sig figs in both molarities while we have 3 sig figs in our volume. So we would want to measure out 0.028 liters or 28 milliliters of that 18 molar sulfuric acid. Now, remember, we do not add water to acids. We add acids to water. We want to make a 1 liter solution. So we're going to add that 28 mils of H2SO, 18 molar H2SO4 to some water in a 1 liter volumetric flask, since that's the amount of solution we want to prepare. We will keep adding water until we get the final volume up to that calibration mark of 1 liter. And then we're going to cap it and we'll invert and mix our volumetric flask to make sure that we truly have prepared a homogeneous solution. Our final example is using a salt to prepare a solution with. We want to make 1 liter of 0.5 molar NiCl2, but the salt is found as a hydrated salt. It has 6 water molecules attached to it. So if we want to prepare a solution from its salt, we want to get the moles that we need to measure out to be the same as the moles that will end up in our final solution. So since we are dealing with a salt, it's a lot easier just to go ahead and work with grams because you can measure out grams using a balance, and we can relate grams directly to moles. So when you have that volume and molarity, we can use those two pieces of information to find the moles of the salt that we want to have present in our solution. And once we have those moles, we can convert them to grams using molar mass. So I take my volume and I take my molarity and I go ahead and convert that to grams using molar mass. You can do these separate or you can do them together. If you do them separate, take care not to round off too quickly with your sig figs. So you have 2 sig figs in your molarity, and that gave me 120 grams when I rounded my answer to 2 sig figs. Now, when you think about finding the molar mass of that hydrate, remember you find it for the Ni and the 2 Cls, and then you add the 6 waters to it. So I need approximately 120 grams to make this 0.5 molar solution that's going to consist of 1 liter. So I'm going to take that 120 grams and I'm going to add to it distilled water. I'm sorry, I left out the IN in distilled water. I'll fix that on the PowerPoint slides. And then I'm going to add that solution to a 1 liter volumetric flask and bring up the volume to the calibration mark with distilled water and cap it and invert it to mix just like you did with the diluted solution. So once you get them in the volumetric flask, it doesn't matter whether it came from a salt or whether it came from a more concentrated solution, the same process applies.